And I also would like to thank our organizers for their tremendous job that they have done to make our work here fruitful and interesting. And now I will talk about the applications of nanoparticles for protection of polymers from UV damage. Polymer I will present the results obtained by joint Ukrainian and Swedish teams. Polymers are everywhere around us due to their very attractive properties, but polymers have serious drawbacks. They are aging with time. They are damaged by the environmental conditions. Among these conditions are chemical species, unfavorable temperature conditions, and also radiation of our sun, especially that part, UV part of radiation. And as so, we need to protect our polymers. There are some methods to protect. They are chemical methods, and people use organic dyes and mix them with polymers, and this shields our polymer from the UV radiation. Unfortunately, the dyes are also degradable, and moreover, they interact chemically with the polymers. So with the development of nanotechnologies, the idea appeared to use quantum dots for protection of polymers. They are quite cheap, and they can serve as absorbers of UV light. In the present study, we focus our attention on the polymer polyvalent polymer. Here is its formula. It's very simple. The list of the advantages of this polymer is very long. Only some of them are listed here. And as always, there is some but. This but is photoaging, especially aging under UV light. So, what did we use for the protection of polymer alcohol? We use well-known quantum dots, cadmium sulfide dots, that absorb UV light, and their properties are to some extent known. How did we make our samples? This is the scheme of the synthesis. We started with the water solution of polymer, and by sequential addings of different precursors, we obtained colloidal solution containing quantum dots. Afterwards, this colloidal solution was dry, and we got some thin films of composites. You can see the thermicroscopy of this colloidal dots. The average size was 5.4 nanometers, and the volume share of the dots in the polymer was as low as 0.3%. Then we subjected our polymers, our nanocomposites, already and a polymer as a reference sample, to the UV light. In order to accelerate the process of degradation, we use laser, we use high powers, because usually degradation takes a lot of time. What can we see? The next slide will be the undeniable evidence that we achieved our aim. Here you can see the left panel from your side. The left panel is the photo of the pure polymer, and the black spot on it is the place where laser beam hit the surface. You can see that the polymer is strongly damaged. The right panel is the photo of the nanocomposite subjected to the same exposure. If you can see, I can see from here, there is a little bit yellowish, more yellowish spot, but it's not too easily to distinguish. So, this is a proof that we have protected our polymer from UV damage. What about the composite? 2 and 2 prime are the spectrum, transparency spectrum of our pure polymer and nanocomposite. You can see that there is some background, but the changes are much smaller. And what we did not have seen by the naked eye is the influence in the UV region. Here is the plot of the absorption in the UV region. Line 1, absorption of pure polymer before irradiation. Line 2 shows the very wide and very strong absorption that appears after the UV irradiation of the polymer, not loaded with nanoparticles. So, this slide and the previous, what do they show? They show us that in the whole gap, homolume gap of our polymer, we have formed a lot of defect states that are related to UV damage. Moreover, we can characterize these defect states by photoluminescence method. The upper panel is the photoluminescence of pure PVA and pure PVA after the UV treatment, and you can see that the defect ensemble of defects in the polymer is strongly changed. The luminescence increases by more than 25 times and also shifts. Contrary to what we observe in the pure polymer, the nanocomposite shows almost no sign of changes after the UV irradiation. Moreover, we don't see a lot of radiation from pure polymer, from the matrix. So it's somehow transferred to the nanoparticles. What goes on within the sample, especially in the pure sample under the UV irradiation? Being absorbed, this high energy quantum of UV can break some chemical bonds. The most known reactions are the scission, the cutting of the chain, and then you have two defects at a time because this is the ends of the chain. You can also break the bonds and create unsaturated CC bonds within the sample, and any other combinations of these two and more, but we will not discuss them. So what goes on in the sample with nanoparticles? Most obvious way to protect is the same way as you use when you protect the polymer with organic dyes. Nanoparticle absorbs UV light, thus screening your polymer from the UV. Then this energy is dissipated either by non-radiative processes or by radiation of this visible light that we have observed. Another not that straightforward way is caused by the additional role of nanoparticles. I have told already that volume share of nanoparticles in our nanocomposite is as small as 0.3%. So all the polymer cannot be screened from the UV radiation by nanoparticles. Polymer has to absorb UV in those places that are not shielded. The excitation, as it often happens in the polymers, migrates along the chain, and when it encounters the nanoparticle, so PVA absorbs, is excited, excitations move along the chain, and then it meets nanoparticle. The homologue gap of PVA is as big as 6 eV. The band gap of nanoparticle is about 3, even less eV. So this is an effective drain for excitation. The excitation of PVA is another after their energy was drained to nanoparticles, it's dissipated by the same route. And now the conclusions. We demonstrated that incorporation of nanoparticles into the polymer improves their UV stability. The role of cadmium sulfide nanoparticles is as follows. First of all, we diminish the probability of photoinduced reactions. Why? Because we have direct absorption by nanoparticles and we have excitation drain to nanoparticles. And how their dissipation occurs, the dissipation of energy occurs about both non-radiating and radiating processes. Thank you for your attention.
Thank you very much. There are questions?
Why did you choose polyvinyl alcohol? If you choose more practically used polymers, for instance, used for greenhouses all over the world, would you obtain the same effect or different?
Most probably we will obtain similar effect. But why did we use polyvinyl alcohol? What is your point that you say that it is not very widely used? Polyvinyl alcohol is used very widely. First of all, you could eat it during your breakfast in the yogurt. Do you know it? Maybe in your house you have polyvinyl alcohol.
In this case, it is not exposed to sun.
Yogurt? Okay, when it is here. But when it is, okay, maybe you are not the person who eats a lot of sweets, but you know these cakes with this whipped cream. They add polyvinyl alcohol into it. Sorry. And then you have this blood substituting medicines based on polyvinyl alcohol. Yes.
Yes, but sorry.
Yes.
To include into this stuff very toxic material, which are quantum dots. Probably I would eat them and allow them.
You will not cope with it. So, actually, it was like in your case. We were working with people who were synthesizing nanoparticles. And one of the ways to synthesize cadmium sulfide is to use polyvinyl alcohol. To be honest. So, polyvinyl alcohol was used for the synthesis. And we were looking for any applications. And one of them was on the surface. The composite. No idea. Probably yes. But since the polymer is bounded by a degradable 0.3%, will it spoil it even? Okay, and the films of polyvinyl alcohol are used for wrapping your food. You know? One of the things. Maybe I use something more, impressive when you eat it. But nevertheless.
Okay.
Question. It's very interesting. What could you find a way to stabilize polymers? But I think it's a global problem to fight this polymers pollution all over the world. So maybe you should know ways to degrade this polymers effectively.
It was not our task, but I know that there are, when I was checking literature, I know that there are ways to get rid of the waste of textile production. They use polyvinyl alcohol a lot for sizing of the materials. So there are some publications